So, ladies and gentlemen, you are all welcome to my YouTube channel. Today, we are going to look at alkane. And as you can see clearly, this PowerPoint is made by Mr. Amit Z. Chowdhury, Department of Pharma Chemistry, LM College of Pharmacy, India. So, for today's lecture, I'm going to actually deliver on alkane. These are the content. We are starting with the definition of the alkane, the structure, the hybridization of the alkanes, which is sp3 hybridization, the general method of variations, and then the general reactions and the uses of alkanes. So now I'm starting with the definition. So what is alkanes? Alkanes are a cyclic branch or unbranched hydrocarbons having a general formula of CnH2n plus 2. So it means that in alkanes, they can be acyclic, because when you said acyclic, it means that they are linear. They are linear. And then at the same time, they can be branch, they can be linear, branch or unbranch. So when you said acyclic, it means that they are not in a cyclic form. You can have them in a linear form. Like this. You can have it like this. It's a linear. So this is unbranched hydrocarbon, and it can be a cyclic branch. So it can be acyclic, like this one is acyclic, so it can be branch. It can form a branch. So this is alkane. So alkane can be a cyclic branch or unbranched hydrocarbons, and they have a general formula of CnH2n plus 2. So that is why, like for example, this n is always a whole number. So if you have, let's say you have n is equal to 1. So if you have n is equal to 1 and you now substitute it in the formula, are now going to have C1H2 times 1 plus 2. So then at the end, we are going to have C times 1, we have C, then H, we have 2 times 2, sorry, 2 times 1, we have 2 plus 1, then we have H4. And this is methane, which is the first member of alkane. And of course, alkanes, they entirely consist of hydrogen and carbon only, because that is why they are called hydrocarbons. So when you said hydrocarbons, from the knowledge of biochemistry, it means that, from the knowledge of chemistry, it means that hydrocarbons are compounds that contain carbon and hydrogen only. So it means that when we are talking about alkanes, the first thing that will come into your mind is that hydrocarbons or alkanes are hydrocarbons. They are hydrocarbons, and they can be linear and they can be branch. So alkanes are hydrocarbons, meaning that they contain carbon and hydrogen only. It means that whenever you see a compound containing carbon, hydrogen, and any other element apart from the carbon and hydrogen, it tells you that that compound is not an alkene, or is not hydrocarbon in general. So therefore, hydrocarbon, they contain only carbon and hydrogen. So alkanes are saturated. At the same time, they are entirely consisting entirely of hydrogen atoms and saturated carbon atoms. So what is saturated carbon atoms? When you say saturated carbon atoms, it means that in alkanes, all carbon to carbon, they have single bond. They are not deficient in any hydrogen atoms. It means that they are made of single bond across each and every carbon in the alkane. So their bonding is single bond. It means that they are saturated and they are not deficient of any hydrogen atoms. And the simplest saturated hydrocarbons made up of carbon and hydrogen. So it's the simplest. And it has its synonyms. It has its synonym. The synonyms of alkanes, you can call it open chain saturated hydrocarbon. You can call it open chain saturated hydrocarbon. You can also call it acyclic saturated hydrocarbons. And you can also call them paraffins. So it can be open chain saturated hydrocarbons. It can also call acyclic saturated hydrocarbons. It can also call paraffins. So it means that at this point we are able to understand that alkenes are saturated. That is one, they are saturated, meaning that all carbon to carbon is single bond in alkenes, and they are hydrocarbons. They are made up of carbon and hydrogen only, and also they are acyclic. It means that they have open chain. They have open chain, and they have a general formula of CnH2n plus 2. So that is alkene. And then the next thing apart from this, then we are now going to look at the hybridizations of alkenes. So generally, if you look at the carbon, if you look at the carbon in alkenes, they have, remember, carbon have atomic number of 6. So if you are going to draw the electronic configuration of this carbon using orbitals, if we are starting with 1s2, then we have 2s2, and then we have 2p2. And of course, the p orbitals from our basic knowledge is divided into 3 subshells. We have px, we have py, and then we have pz. So it means that in this, because this is in a ground state, So at the ground state, the px have 1 electrons, and the py also have 1 electrons, but pz have 0 electrons in the ground state. So that is why if you look at it here, this is the energy and this is the ground state. So at the ground state, you see here you have 2s. So this is the 2s here because they have the same energy level. That is why we are just considering 2s and 2p. So the 2s have 2 electrons. Look at them. This is the first one that move at the clockwise and the other one and in the anti-clockwise direction. And of course, the 2px have 1 electrons, and then the 2py have also 1 electrons, and at the same time the 2pz have 0 electrons. So that is at the ground state. But in the excited state, because the s and the 2s and 2p have the same energy level, so it means that there is a possibility that 1 electron from 2s can jump. It can jump to the pz. So that is happened. That is what happened here. So you see here we have 2s but 1. So you have only 1 electrons here, and then here 1 of the electron from this 2s is now jumped to pz. So it means that we have 2s, and then we have 2px1, 2py1, and then 2pz1. So in the excited state, 1 electron from 2s is jumped from this 2s to 2p. So that is what happened. It means that we have 1s2 in the excited state, then we have 2s1, and then 2p3. So 1 electron from here is jumped to this, and at the end our pz also get 1 electrons. So it means that we have py, we have py, so the px1, py1, pz1. So then we have 1 electrons also at we have also 1 electrons at US. So if you add these orbitals, if you add all of them, we have 1s, then we have py, so the px plus py plus pz plus pz. So px plus py plus, so we have s plus px plus py plus pz. So if you add them all together, you have 1s, then you have 3p. So that is why we have sp3 hybridization. That is how we arrive at sp3 hybridization. And of course, remember when you said hybridization is a combination of 2 or more, it is a combination of 2 or more orbitals to produce what you call hybrid orbitals that have a characteristic or feature that is differ from the individual orbitals if you take them. Like for example, S have spherical shape, P have dumbbell shape. So, but if you have sp3 hybridization, it is neither spherical, neither bell shaped. So that is what happened in hybridizations. You have different orbitals joined together to produce hybrid orbitals. So in this case, you have one s and you have three different p orbitals, which is px, py, pz, and after you add them, then it gives you sp3 hybridization. So that is hybridization of alkanes. So the hybridization of alkanes is sp3 hybridization, and they have the bond angle of 105.9 degree. So now the sp3 hybridization, the shape of sp3 hybridization, it is of course tetrahedral. The shape of sp3 hybridization of alkane here is tetrahedral. It is tetrahedral. It is tetrahedral. It has a tetrahedral shape. And of course, the percentage of S character is 25%, and the percentage of P character is 75%. And how do we get this? It's actually after you have sp3 hybridization. So now you want to calculate the percentage of S. So how many S do we have? Is 1. And then you now take the total number of orbitals in the hybrid orbital. So you have 2 plus 3p making 4. So 1/4 times 100, and that is how we arrive as 25%. And then of course for the this one is for the S, and then for the p orbitals also, if you are going to do it, we have 3 different p. So we have 3 divided by 4 times 100. So after you do it, then we are now going to get 75% of p character. So this is how the percentage is being actually calculated. And the bond angle of this sp3 hybridization of alkane is 109.5 degrees. And of course, if you now look at the shape of the sp3 hybridization, is differ from the individuals orbitals S and the P. So now we check now methane. So methane, if you now look at the methane, it also has sp3 hybridization. Of course, methane have 1 carbon and 4 hydrogen, and they have a bond length. They have a bond length between carbon to hydrogen, have a bond length of 1.10 Armstrong units. 1.10 Armstrong unit, and of course, the bond angle is 109.5 degrees. So now the next thing that we are going to look at is actually the free variations of alkanes. How do we get alkanes? How do we obtain alkanes? So alkanes are produced first by catalytic hydrogenations of alkenes or alkynes. Remember that alkenes are also hydrocarbons, but alkenes have between 1 or 2 of their carbon have at least 1 double bond. They have at least 1 double bond in the case of alkenes. That is one of the feature or the functional group of alkenes. So alkenes, they have a feature of at least 1 or 2 of their carbon must have a double bond. And if you have carbon to carbon double bond in that carbon bearing the double bond, it means that it is deficient of 2 hydrogen. It means that it is deficient of 2 hydrogen. And in the case of alkynes, they have a functional group of carbon between carbon to carbon is triple bond. So it's triple bond. So in the case of alkynes, they have deficiency of 4 hydrogen. They have deficiency of 4 hydrogen. That is -4. And this one is -2. That is deficiency of 2 hydrogen. So alkenes have deficiency of 2 hydrogen, and alkynes have deficiency of 4 hydrogens. So when you undergo catalytic hydrogenation, when we said hydrogenation, what is hydrogenation? Hydrogenation, it means addition of hydrogen. is the addition of hydrogen. So here we said catalytic hydrogenation of alkenes. It means that if you have alkenes using a catalyst, and the catalyst used here is nickel. And remember when we said catalysts are substances that speeds the rates of biological or chemical reactions in general. So catalysts are substances that speed the rate of the reaction and they do not consume. Generally, these catalysts speed the rate of the reaction by decreasing the activation energy. So the catalysts catalyze the rate of the reaction or increase the rate of the reaction by increasing the activation energy. So in this catalytic hydrogenations, there are some conditions that you must expose to your reactant first. You need a nickel, which is a catalyst, and you need heat. This means heat. So you need heat and you need a catalyst. So the catalyst here used is nickel, but apart from the catalyst, apart from the nickel, you can also use PT as platinum. You can also use palladium. So all these are the catalysts that are used in catalytic hydrogenation of alkenes. So therefore now in this case, in the first reaction from alkynes to alkene, it means that it's like you are following a degree of saturation. Like if you add two hydrogen atoms, if you add two hydrogen atoms in alkynes, you are going to get alkene by breaking down one of the pi bond. Remember, whenever you have a pi bond, it means that you have or whenever you have a pi or whenever you have a triple bond, it means that you have a pi bond, and then you also have a sigma bond. So like in this case, we have three double bonds. So you have the triple bond. So in this triple bond, the middle one is sigma bond and the two side-by-side bonds are the pi bond. So in the case of the first reaction, you are adding hydrogen atoms. So when adding these hydrogen atoms, you are breaking one of the pi bond. Then as a result of that, you will have something like this. You will break this, and then first here there is one hydrogen atoms, and here there is also another hydrogen atom. So you are going to break this. Then at the end, one hydrogen atoms will be added, another hydrogen will be added here. But still, there is another one pi bond. So here it means that we have we have one double bond. So we have double bond. So from triple bond, we are moving to double bond. So you are converting alkyne to alkene. You are converting alkyne to alkene. And then the next reaction here is this. Then another hydrogen atoms will be added across this. So therefore, at the end, we are going to have something like this. So we have hydrogen here. Another hydrogens also will be added here. Of course, here there is another hydrogen. And there is another hydrogen. So if you look at this now, there is no any double bond. They have single bond. So it means that alkyne is converted to alkene, and then from alkene with a single bond. But across this process, you need to heat it. You need a catalyst, nickel. Nickel is needed before the reaction or before you are able to get your final product. So it means that if you look at it here from alkenes, alkynes, you can get or you can obtain or you can synthesize alkanes. So alkanes are preferred or are produced in the laboratory using alkyne as a substrate or using alkyne as a reactant, catalyst, and then you heat it. It means that first, if you want to get it, you need to have your container. You add your alkyne or alkene. You can use alkyne or alkene. Let's say this is your container. In this your container, let's say you have your container like this. So from this your container, let's say this is the container, and in the container you first add alkene or alkyne. So you add your alkene, and then you add your nickel, and then you heat it. You heat it. Plus heat. and then you will obtain your alkane. The alkane will be obtained. So that is the preparation of alkanes using catalytic hydrogenation. So like for example, we have reactions that is used in conversion of unsaturated fatties to saturated fatty acids. So like saturated fatty acids, they are fatty acids that have carboxylic group, functional group, and they have double bond in some of the alkyl chains. So if you add hydrogens across them using a catalyst, then you can actually obtain your saturated fatty acids. So this is an example. We have hex 1 in, it's an alkene. So it has one double bond at carbon 1. So if you want to get actually hexane, which is a solvent, then you need to add hydrogen, nickel, then you add or you heat it. Then after that, then hex 1 in will be converted to hexane. So this is how we obtain alkane from the catalytic hydrogenation. Remember, hydrogenation is the addition of hydrogen. Okay. So the next thing is preparation of alkanes from alkyl halides. Alkyl halides. When we said alkyl, what is alkyl? Alkyl, remember, is one of actually a group that when one hydrogen atoms is reduced from alkane, then you will get alkyl. Like for example, we said we have methane, which is CH4, but the alkyl CH3. The alkyl group of methane is CH3 by reducing only one hydrogen atom. So it means that this is methane, but this one is methyl, and you can have like C2H6. C2H6 is ethane. Then it can change to C2H5, which is ethyl. So it means that one hydrogen atoms is reduced. So when you said alkyl halide, it means that when you have alkyl plus halogen member, the halogen members can be halogens. This X stands for halogens. So halogens member can be fluorine, can be chlorine, can be bromine, can be iodine, and it can be astatine. So these are the members of halogens. So you can obtain alkane from these alkyl halides. So like for example, here you have alkyl halides, then you now react it with magnesium plus dry ether, then it will give you what we call organomagnesium reagent. Organomagnesium reagent. This organomagnesium reagent is called Grignard reagent. It's called Grignard reagent. So it means that in the case of this alkene or alkane can be obtained from Grignard reagent, and this is the Grignard reagent. So in the Grignard reagent, after you add water molecules, then you are going to have because this is alkyl, and then you have hydrogen added. So you can get it from here. So Grignard reagent can be used to get or to obtain alkanes, and the method is called Zere-Witty-Nobst method. Zere-Witty-Nobst method. So you can get that actually. So from alkyl halides, you can get alkane. These are like, for example, let's say the R here is CH3. Like for example, CH3. Then you now add hydrogen. So it means that you have CH4, which is methane. So in this Grignard reagent, because this alkyl halide is given as an example, so you can have something like, let's say R, it can be C2, H6, then magnesium, then you have X here. That is X. This is what I mean. You have C2H6, sorry, not 6, H5 is supposed to be 5 here because it's alkyl. So here is 5. Then you have magnesium, Then we have, let's say we have chlorine. So this is a typical example of Grignard reagent. So in this Grignard reagent, after you now add, you have your water, after you add the water molecules, then it's going to give you C2H5, and then one hydrogen will be added. Then at the end, we have C2H6, which is ethane. So from alkyl halides, from alkyl halides, you can get alkane. At the same time, alkyl halides, you can also get alkene from alkyl halides using zinc as a catalyst plus free hydrogen. So this is also another reaction. It means that under these alkyl halides, you can get alkanes by using alkyl halides Rx in the presence of free hydrogens and zinc. So therefore, we can also synthesize alkane using zinc and free hydrogen. So you can have, if you have your alkane like this, alkyl halides Rx, then in the presence of zinc ion plus free hydrogen, then you are going to have your alkene plus zinc 2 plus, then plus free chloride ion. So it means that in this case, let's say you have the alkyl halide, let's say you have methyl bromide. So methyl bromide in the presence of zinc 2 plus, then plus free hydrogen, then you are going to have CH3. Then this hydrogen will be added here, CH3H, then plus zinc 2 plus, then plus plus the bromide ion, So when you have this, then CH3C, it means that you have CH4. So from methyl bromide, you can get methane. Methyl bromide, you can get methane. So that is in this case. And this is also another like Grignard reagent, but in this case, we are using lithium in the case of, in place of, this is Gilman reagent. So in the case of this Gilman reagent, you are using lithium instead of magnesium. So that is why it's called a Gilman reagent. So in this Gilman reagent, you have, first you have your alkyl halides, then you add lithium and the dry ether, then you are going to have your Gilman reagent. So this Gilman reagent in the presence of copper halides, then will now react to produce the Gilman reagent. So the Gilman reagent will now further rearrange itself to produce the alkane. So this under alkyl halide, we have three ways. First, using this method, and then second, this one, and the last one, this. So this is how to get alkanes from alkyl halides. So you see at the end here, we get alkanes. At the end here, we also get alkanes. And at the end here, we were able to get alkanes too. So now, the next types of the method of the preparation of alkane is Wurtz reaction. So Wurtz reaction, in the Wurtz reaction, you are using alkyl halides. This is, you have two molecules of alkyl halides. Then you now react it with sodium metal in the dry ether, in the presence of dry ether. Then you are going to get your alkane. Let's assume, let me just give an example. Let's say you have two molecules of, let's say CH3 bromides, then plus sodium, plus two molecules of sodium. So in the presence of dry ether, in the presence of dry ether, in the presence of dry ether, we are going to get CH3, CH3 plus 2 molecules of sodium bromides. So at the end, if you look at this, we have what we call ethane. This is ethane. So this is how we get alkyl halides using Wurtz reaction methods. So produce double number carbon products than the parent haloalkanes. So this is a double number carbon products. And of course, this is the mechanism. So there is a mechanism. So in the step 1, single electron transfer, that is SET. So from this, there's a single transfer of the alkyl group, aryl group to the sodium, and then you generate a radical. And then the radicals will now react with sodium ion to produce carboanion. So these carboanions using the SN2 reaction mechanisms, we are coming to that. We also do a video on SN1 and SN2. So using SN1 mechanisms, the alkyl halides, using SN2 reaction mechanism, the alkyl halide react with the carboanions, and then you generate your alkenes. So this is Wurtz reaction. So you see, this is the mechanisms. First, a single electron transfer from a sodium metal to alkyl halide, which dissociates to form an alkyl radical. And then second set gives a nucleophilic carboanions. So these carboanions then attacked another molecules of alkyl halide in a nucleophilic substitution reaction, that is SN2, to form the final coupled products. So this is what happens, like for example, and the limitation is only used for the synthesis of symmetric alkenes. Yeah, it's only used to synthesize symmetric alkenes, the alkenes that are symmetric, that are the same. That is the limitation of Wurtz reaction. So the next thing is preparation from carboxylic acids, and we call it Dumas decarboxylation. Dumas decarboxylation. So in the Dumas decarboxylation, you have, like for example, here you have a soda lime, sodium hydroxide plus calcium oxide, and then you now react it with acid salts. So after you now react it with the acid salt in the presence of heat, then we are also generating alkyl halides. So this is Dumas decarboxylation. When you say decarboxylation, it means removal of carbon dioxide. So that is what happened here. So this sodium react with this, then we have 2 of this, then we have CO2 plus this oxygen, and making CH3, and from plus free calcium ion. So that is what happened. And we also have another from the carboxylic, after preparation from carboxylic acids, there is also what we call, apart from the Dumas decarboxylation, because when you said decarboxylation, it means removal of carbon dioxide. So we also have Kolbe electrolysis. So during the electrochemical oxidative decarboxylation of carboxylic acids, this is the carboxylate salt. So during electrolysis, then you are also going to generate alkene. For example, at the anodes and at the cathodes. So what happened at the anode? So at the anode, there is an oxidation. Oxidation is generally taking place at the anode, while reduction at the cathode. So you generate at the anode, you generate your alkene. At the anode, you generate your alkenes. So we have Dumas method and Kolbe electrolysis under preparation of alkenes from carboxylic acids. Okay. And of course, clearly from the Kolbe method, synthesis of the alkanes is taking place exactly from their anode. Okay, then the next thing is from aldehyde and ketones. So you can get it from aldehydes and ketones. So we have what we call Clemmensen reduction. Clemmensen reduction. So the Clemmensen reduction, an acidic solution of zinc dissolved in mercury. That is amalgamate of zinc as the reducing agent. So here we use zinc amalgam, which serve as a reducing agent in the presence of hydrochloric acids. So amalgam or amalgamate of zinc fluoride, and the hydrochloric acid in their presence, you can generate alkanes from ketone. This is ketones. This is ketone. So it means that in the presence of ketone, so you can convert ketones to alkene in the presence of zinc amalgam and hydrochloric acids. Like for example, let's say you have oxygen, carbon, you have oxygen, carbon to oxygen double bond, and we have, let's say, CH3 here, and we have CH3. So in the presence of zinc amalgam, hydrochloric acids, and you are now going to generate CH3. So this is what you are going to generate at the end. So we get ethane. Then apart from the Clemmensen reduction, there is also Wolff-Kishner reduction. We have hydrazine. So hydrazine is used as a reducing agent under basic condition. So this is the hydrazine. So this is the hydrazine, and in the presence in a basic medium, the ketones also generates alkane. So ladies and gentlemen, this is the general method of preparation of alkanes. General method for the preparation of alkanes. So the next thing is actually reaction, is the reactions of alkenes. But this reaction of alkenes includes first, we have halogenation. We have halogenation. When you said halogenation means addition of halogen members, which usually happen in the presence of UV light, that is ultraviolet and heat, and we also have nitration, addition of nitrogen 4 oxides. We also have sulfonation, that is addition of sulfuric acid. Then we have oxidation. Then we also have pyrolysis / cracking, as a breaking down of large alkane members into smaller one. So now, let's look at, so we are starting with the cracking of pyrolysis. So the definition, when you said cracking is a chemical process by which heavy, that is the larger hydrocarbons molecules, are breaking off into lighter molecules by the means of heat, and usually pressure and sometimes catalyst. So in the presence of heat, high pressure, and catalysts, the larger hydrocarbons are breaking down to produce smoother. So compound decomposition by the action of heat alone is known as pyrolysis. So if you have a compound and the compound is decomposed, that is breaking down using just using heat alone, so it's called pyrolysis. But for the cracking, you need heat, pressure, and also catalysts. So, and then what is the major use of this cracking and pyrolysis? It's used in petroleum refining. So cracking converts straight chain hydrocarbons that are poor fuels into branch compounds that are higher performance fuels. Of course, in petroleum, when you have a petroleum and it has a linear chain hydrocarbon, it means that the fuel is not good, it's a bad fuel. But using a cracking method that in refinery or that we are using it in the refineries, you can convert this red chain hydrocarbon into a branch change, and the branch change compound is the one that is when it is found in the fuel, it means that the fuel is of high quality. So, and then the next thing is, of course, let's look at the cracking itself. So under cracking, we have thermal cracking. So in thermal cracking, we use high temperature and pressure, that is thermal cracking. And then in catalytic cracking, the process using catalyst. So it utilizes the use of catalysts such as sulfur 4, silicon 4 oxides, aluminum oxides, and zeolites. So this is the thermal cracking. So sorry, catalytic cracking. So in catalytic cracking, we use a catalyst, and in the hydro cracking, then we use it's like a catalytic cracking with hydrogenations, using hydrogen and used to produce a gasoline in high yield. So this hydrocracking is like a catalytic cracking that use hydrogenation reaction, that is addition of hydrogen to produce gasoline that is of high yield. Then we have steam cracking, that is using steam that is of temperature of 700 to 900 degrees centigrade, followed by rapid cooling. So the low molecular weight alkenes obtained from these cracking processes can be separated and purified and are the most important raw materials for the large-scale synthesis of aliphatic compounds. So during this cracking process, usually a smaller alkanes molecules are also generated. So those smaller alkanes, they are used, or they are purified and separated. And then it's now used as a raw material for the synthesis of aromatic compounds. So this is cracking. So in the cracking, starting with the pyrolysis. So pyrolysis of alkanes. First, there is a generation of free radicals. So examples like this is propane. So in this propane, first you break the propane into two radicals. So you generate a radicals, and these two radicals also react with another molecules of alkane. So you have methyl radical react with another molecules of propane. You generate methane plus another radicals. And the radical generator also break down to produce alkene plus free hydrogen. Sorry, to produce methyl plus free hydrogen. So the free methyls now also further react to generate ethene plus free hydrogen, and the free hydrogen from generators from this step and these steps now react to produce a molecules. So see, this is how the pyrolysis is taking place. It's like you are generating radicals, and then subsequently you now generate a final products like alkene and free hydrogen. So that is the propane hydrolysis. So the reactions, we are starting with halogenation of alkane. So in the presence of ultraviolet, right? In the presence of ultraviolet lights and heat, the chlorine reacts with reacts or the alkyl halide or the halogens react with alkene in the presence of ultraviolet lights and heat to generate alkyl halides, and the reactivity of chlorine is greater than that of the bromine molecule. So halogenations refers at tertiary carbon, then secondary carbon, and then primary carbon. So it means that halogenations is higher when you have tertiary carbon, followed by secondary carbon, and then lastly primary carbon. So in these halogenations, there are mechanisms of this halogenation. There is chain initiation. First, there is a chain initiation. And in this chain initiation, there is a hemolytic cleavage of sigma bond. So the sigma bond is being cleaved to generate halide radicals. And we have chain propagation, which actually involve the conversion of one to another radicals. So you see in this case, you have free radicals first generated as halides, and then these halides now react to produce hydrogen halide plus methyl radical. And these methyl radicals react with another molecules of halogens to generate alkyl halide plus free halide radicals. And then we have chain termination. So the free methyl radicals and the free alkyl radicals react together to produce alkyl halides. And then the free methyl radicals react with another free methyl radicals to generate alkene. And then the free halide plus another free halide react to produce a molecule. So it means that in chain termination is actually when there is a conversion of the free radicals to normal molecules. So in this case, it's the radicals that's joined to produce the molecules. But in the other case, which is the chain propagation, to involve the conversion of one molecules to another radical. So in this halogenation, there is a transition state. There is a transition state where a carbon acquiring a free radical character. This is the reaction progress. So then the next thing is examples of this. We have chlorination of propane. So here you have propane, then you add chlorine, then we have abstraction of primary hydrogens. Then at the end, you end up generating N-profile chlorides. And then the second one, you are adding it as the primary carbon. The hydrogen is added at the primary carbon. That is why we have normal propyl chlorine. And in the second reaction, it means that two products are generated. So the hydrogen is added, the chlorine is added at the at the secondary carbon. So that is why we have isopropyl chlorides. The first one, the chlorine is added at the primary carbon. That is why we have normal propyl chlorides. And the second one is added to the secondary carbon. And that is why we have isopropyl chlorides. So it's like an isomerization. The compound, well, we have the same molecular formula, but in terms of structure, they are different. So the rate of these abstractions of hydrogen atoms is increasing from tertiary, secondary, and primary. Okay, so now